Okay, so the next thing that you need to know about these BJT transistors is the fact that basically the collector current is always larger than the base current. So I write it down here, the collector current is larger than the base current. And of course, it wouldn't make any sense if it were different, because otherwise there would be no point in using a transistor, really, because you want to use the current gain of the transistor. You will understand what I mean by this. So there is something called the current gain. There is something called the current gain of the transistor. And the current gain of the transistor which is also denoted by beta, is basically the ratio of the collector current to the base current of the transistor. Meaning that you basically calculate the collector current and calculate the base current. Either you calculate them or you measure them, basically using, for example, some ammeter or something like that, and then take the ratio of the two, and that becomes the current gain of the transistor. Of course, this current gain, or your beta, which is also sometimes called H of Fe, is something that you can look up in the data sheet of your transistor as well. For example, for some transistor your beta is 50, for some transistor is 100, for some transistor is 20, 30, and so on and so forth, depending on what sort of transistor you're looking at. And what that means is that, for example, if your beta is equal to 50, then your collector current is always going to be 50 times the base current. Whatever the base current multiplied by 50, that becomes your collector current, right? Of course, provided that your transistor is fully turned on, which is something that we will get to in just in a short amount of time. So what you need to understand from here is that the collector current, your I of C, is always greater than your I of B, right? And the ratio of these two, basically I of C to I of B, is basically called beta, or the current gain, of your transistor. That's basically what you need to understand from here. And of course, you can see that you can play with these. Basically, your beta is always constant. You cannot change that. It comes as a physical characteristic of your transistor, meaning that depending on the changes that you have in the base current, you can cause some changes in the collector current of your transistor, meaning that you can write this as beta times I of B is equal to I of C. So this beta is constant. You cannot change it. The higher your I of B, the higher is going to be your I of C, meaning that, for example, your I of B, take it as whatever it is, it's multiplied by beta, and then as a result you will get some I of C on the other side of the equation. So that way you can actually basically control the collector current of your transistor. And So for example, suppose that for example the base current is 1 milliamp. So there is some transistor in some circuit, your base current is 1 milliamp, and for example the collector current is I of C is 150 milliamp, right? So what is the current gain of this transistor? What is your beta? So you know that your beta is equal to I of C to I of B, which is basically in this case 150 milliamp to basically 1 milliamp. Milliamp and milliamp you can cancel out. That's equal to 150. That means that your beta is equal to 150. So that means that your collector current is always going to be 150 times your base current, right? Now there is a lot of discussion. There is some that you can there can be basically some discussion about what actually happens inside the transistor when basically when it basically turns on and then the basically those two diodes, one of them was reverse biased, and as we connected the base current, as we basically as the base current started flowing, that reverse biased diode was not a problem anymore. But I suppose that's not really important right now. The important thing is to understand that basically whenever the base current is flowing, the collector current can be flowing, and then you can use that property of the transistor for whatever sort of purpose that you want to, that you have, basically. So now suppose that for example you have some transistor in where for example your I of C is equal to, for example, 2 amps, and your beta is equal to 20. Your beta is equal to 20. You want to know what is your I of B, what is the I of B that you need in this case in order to get 2 amps of current as your collector current. And of course, based on the fact that we said that basically beta is equal to I of C to I of B, so this means that basically I of B is going to be 1/20th times 2 amps, which means that you can basically write beta is equal to I of C to I of B, and that basically means that 20 is equal to basically I of C, which is equal to 2 amps, to I of B, which means that basically I of B times 20 is equal to 2 amps, which means that I of B is equal to basically 2 amps by 20, which is equal to 1/10 amps, which is equal to 100 milliamps, right? Which is equal to 100 milliamps. That's basically how you use this relationship between I of B, I of C, and beta in order to calculate any one of them if any two of them if the other two of them has been given to you, or if you have the possibility to measure any of them. Of course, the beta is something which is a physical characteristic of the transistor. You can look it up on the internet, on some website, for example. I of B and I of C, you can always basically I of B, you have always control over that, meaning that you can, depending on the voltage and the resistor that you choose for your base, there is some current flowing as your I of B, and then based on that and your beta, there is some I of C on the output of your transistor, basically. So that is basically the Now suppose that you have this circuit over here. You have basically a you have a circuit over here, and you have an NPN transistor over here. You have this collector connected over here, and that the emitter is basically connected to ground, meaning that this is your negative and this is your positive, right? And this is your, of course, this is your R of B, and this is your R of C, and this is an NPN transistor, right? So that means that you have basically forward bias the base emitter diode over here, and then the collector has been connected to the positive pole of the power supply, meaning that your circuit is working no problems. Now suppose that this voltage is 10 volts and this resistor is 100 kilo ohm, and suppose that this R of C is equal to 1 kilo ohm, right? And the beta of this transistor is equal to 50. And you want to know basically what sort of voltage you have over here. Let's call this, for example, V of C, right? Let's call this V of C. Now, in order to calculate, for example, this voltage over here, and this is important because of many reasons. We will get to the reasons later, but for now, let's bear with me and understand how to calculate this voltage, and then we will be able to use this in order to actually turn the transistor on. Otherwise, if you don't know how to calculate this voltage, you would not be able to turn the transistor on, right? So basically, in order to be able to calculate this voltage, there is basically the voltage up here is 10 volts. That you already know, right? That means that, and this is the ground, so there is 10 volts across these 2 points. And the 10 volts are across the collector emitter junction of the transistor and across this resistor over here. So if I want to know basically, and this V of C is actually the voltage across the collector emitter junction of the transistor, meaning that when you calculate V of C, you're actually calculating the collector emitter junction voltage of the transistor. So in order to calculate this, basically need to calculate, of course, since the transistor is something dynamic, I cannot regard it as a resistor and just go and say that, for example, there is so much voltage drop across this PN junction, and so based on that, for example, apply the Ohm's law to the PN junction of the transistor. It doesn't work like that. I have to calculate such things not directly, but I have to do that actually indirectly. Meaning that what I need to do is that I need to calculate the voltage drop across this resistor, and then since I know that the whole voltage is 10 volts over up here, meaning then there is some voltage drop across this resistor, and then the rest of the voltage is being, of course, has to be dropped across the PN junction of the transistor, right? So that means that I have to apply the Ohm's law to this resistor over here. And so basically you know that the Ohm's law is V is equal to IR. So the voltage that I want to calculate is V. I is the current going through this resistor, and R is the value of the resistance of the resistor. But now the problem is that I don't know how much current is going through this resistor. And so basically that is basically I of C, right? So I need to calculate I of C first, and then based on that I will be able to calculate the voltage drop across the resistor. So in order to calculate I of C, I can basically use the relationship between the base current and the collector current of the transistor, which was beta is equal to I of C to I of B, right? So since beta is equal to I of C to I of B, if I am able to calculate the base current of the transistor, which is basically this current over here, the current going through the base of the transistor, then based on that I can calculate the collector current, which is I of C over here. And of course I already know that beta is equal to 50. So what that means is that then so now what is I of B? So I already know that there is some voltage drop in the base emitter junction of this transistor because it's a forward biased diode, and a forward biased diode, the voltage drop across that is 0.7 volts. But there is 0.7 volts. The base emitter junction of the transistor. But as we discussed before, I don't have to take that into consideration, because we said that if the power supply is usually, this is what engineers actually do. So when the power supply is greater than or equal to 10 volts, they just simply ignore the voltage drop across these PN junctions, which is usually 0.7 volts, which is assumed to be 0.7 volts. And of course, if you're working with the germanium transistor, of course, then the PN the junction voltage drop would be something about 0.3 volts, which is next to nothing. So that would not be a problem either. So that means that basically I can simply ignore the 0.7 volts base emitter junction voltage drop of the transistor, meaning that I can just simply forget about this whole thing, right? So meaning that I can assume that the whole power supply voltage, the 10 volts that I have over here, is going from the positive pole of the power supply to ground from here. And I can assume that basically the whole voltage is being dropped across the the base resistor of the transistor, meaning that I can say that basically if I apply basically Ohm's law to basically R of B, we have, I can assume that the voltage drop across the resistor is 10 volts, so V is equal to basically I times R. So 10 is equal to 10 volts is equal to I of B times R of B, and R of B is basically R of B is basically 100 kilo ohm, 100 into 10 raised to the power 3 ohm, which means that I of B is equal to 10 volts divided by 100 into 10 raised to the power 3 ohm, right? So 10 by 100 is 1 to 10. This is 10 raised to the power 10 into 10 raised to the power 3 is equal to 10 raised to the power 4. And so that would be 10 raised to the power negative 4 amps, which is the same thing as 0.1 milliamps. So it's because this is 10 raised to the power negative 1 into 10 raised to the power negative 3 amps, which is equal to 0.1 milliamps, right? So I of B is equal to 0.1 milliamp, right? Which is the same thing as 100 milliamp is the same thing as something microamp, which is not important really right now. So now I know that basically the current going through the base is 1/10 of a milliamp, right? So what I can do is that now I can use this relationship here and write beta, which is equal to 50, is equal to I of C, to I of B, which is equal to 0.1 milliamp, which is 0.1 into 10 raised to the power negative 3 amp, which means that basically I of C is equal to 50 into 0.1 into 10 raised to the power negative 3 amp. And that's the same thing as is 5 times 10 raised to the power negative 3 amp, which is equal to 5 milliamp. That means that your I of C is equal to 5 milliamp, right? Based on this relationship. And you can see that basically 0.1 milliamp and 5 milliamp, that's actually 50 times. If you multiply this by 50, you will get this current over here, meaning that the base current is always basically, if you multiply it by beta, you will get your collector current, right? Meaning that the collector current is always greater than the base current, right? Now, what you can do, so now I know what my collector current is, and so I can calculate the voltage drop across this resistor. And again, since the power supply is 10 volts, I can actually ignore the voltage drop across the collector emitter junction of this transistor, ignore it and regard it as 0, and assume that the whole voltage is being dropped across the collector resistor, meaning that if I apply the Ohm's law to the collector resistor, I can say that basically 10 volts is being dropped across the resistor, and then the current going through that is 5 milliamps, 5 into 10 raised to the power negative 3 amps times no, sorry, no, I made a mistake here. I don't actually know how much voltage is being dropped here, but but what I can do is that I want to calculate the voltage drop across this resistor, or V of R of C. And I know that the current going through that is 5 milliamps, 5 into 10 raised to the power negative 3 amps, times R, which is 1 kilo ohm, which is 10 raised to the power 3 ohm. And these two will be cancelled out. You have 5 volts, right? V is equal to 5 volts. That means that there is 5 volts voltage drop across this resistor, meaning that V of R of C is equal to 5 volts. And of course, since this is a series circuit, meaning that this resistor is connected in series with the collector emitter junction of the transistor, you can say that basically you can think of this as V of C plus V of R of C. V of R of C is equal to the supply voltage, 10 volts. Now V of C is equal to V of C plus V of R of C is equal to 5 volts is equal to 10 volts. Therefore, V of C is equal to 5 volts. And there is 5 volts voltage drop across the collector emitter junction of this transistor. And what that means, and of course we will get to that in a couple of circuits, hopefully in this video. And what that means is that since there is some voltage drop across the collector emitter junction of the transistor, you cannot say that the transistor is turned on. The transistor is not yet turned on. You have to still give more current to your base so that there is more current in your collector, and as a result there will be more voltage drop across this resistor, and there will be less voltage drop across the PN junction of the transistor, the collector emitter junction of the transistor. As you can see, basically the voltage drop across this resistor that we calculated to be 5 volts is a function of the current going through the resistor and the value of the resistor. The value of the resistor, of course, is not changing. So the higher the current, the more voltage drop you'll have across this resistor, meaning that the less voltage drop you will have across the PN junction of the transistor. So how can you get more current over here? How can you get more collector current? By increasing your base current, you will get more and more collector current, right? More collector current means more voltage drop across this resistor, and that in turn means less voltage drop across this PN junction. And if you can drive your transistor in such a way that, meaning that if you can supply enough current over here so that there is enough current over here, so that there is enough voltage drop over here, so that there is 0 voltage drop over here, then you can say that your transistor is turned on, and we will get to some example of that as well. Okay, so now basically what I want to show you here is that basically using some parameters, like for example this resistor over here, or this resistor over here, or the beta value of this transistor, and so on and so forth. You have basically the possibility to change the value of V of C, and V of C is basically the voltage across the collector and emitter of this transistor. basically the purpose of all of this is that you have the possibility to get any sort of voltage that you want on V of C, meaning that when V of C is equal to 0, then we normally say that, or technically say that, basically the transistor has reached some phase called saturation. So there is technically something called saturation, and saturation means that the voltage across the collector and emitter junction of the transistor is 0 volts. And you can imagine that basically when you have a closed mechanical switch like this, if you have a closed mechanical switch and if you connect it to a power supply, then if I close the switch like this, of course the voltage drop across this switch is 0 volts, right? The voltage drop across the switch is 0 volts, which means that basically the electrical resistance between these 2 points is 0 ohms, right? On the other hand, if I have a power supply and if I connect it across some sort of resistor, depending on the value of the resistor, you will have some voltage drop across this resistor. And if I have, for example, 2 resistors here, I have some voltage drop here, some voltage drop here, depending on the value of the resistor, and then what that voltage drop I can calculate with V is equal to I times R, right? So if there is a resistor in a circuit, depending on the supply voltage V of S and depending on the resistance voltage, there is some voltage drop across that resistor. But if the resistance of that resistor tends to 0, meaning that gets closer and closer to 0, then of course the voltage drop across that resistor gets decreasing and decreasing and decreasing, because if I keep the current constant here, basically taking the current constant here by reducing the resistance across the resistor, the voltage across the resistor has to come down as well, because this is an equation, right? And that's basically what happens in a mechanical switch. In a mechanical switch, when the switch is open, the resistance across the switch is infinite. When the switch is closed, the resistance across the switch is 0. And therefore, when the switch is closed, then you have 0 volts voltage drop across the resistor. Now you can imagine that basically the collector emitter junction of the transistor that you have here, what it does is that you have you can imagine that this is the positive supply, and from the positive supply you simply go to ground, and your ground is the negative supply of the power supply, right? So you're going from negative to from positive to negative, and somewhere over here you have the R of C, and over here you have the collector emitter junction of the transistor. I show that with a resistor, and basically what that means is that I have the possibility to control the voltage drop across this resistor here using the values that I have here, for example, by changing the values of R of B, R of C, and the beta of the transistor, meaning that if you take some other transistor with another beta value, and basically playing with these three parameters, you have the possibility to change the voltage drop across this resistor here, right? And the less voltage drop that you across this resistor, the more voltage drop you will have across this resistor, and as a result, you will have more voltage here, right? And more voltage means more current, of course, because again V is equal to IR. The more voltage that you have, the more current you will have, taking the resistance constant. And the more voltage drop that you have here, the less voltage drop you will have here. That means that the voltage keeps decreasing here, and then the current keeps decreasing here, and then using that you can basically put some, whatever sort of load you have, you can connect it to the positive rail of the power supply here, and then another end to the negative end of the power supply. And then using this circuit, you can control what sort of voltage and what sort of current your load is going to get. So for example, suppose that you have a lamp over here, and you can using basically again these three parameters, you can basically control the voltage and the current that the lamp gets. If the lamp is basically in the collector lead of between the collector and the positive power supply, or even if you put the lamp over here, the same thing would happen, of course. So the purpose of all of this is to have some control over this voltage here in a dynamic way. And if you can do that, then you can put any sort of load here, and then you can set the voltage and current of that load to any value that you want. And of course, they do the same thing. Using, for example, photocells. They put a photocell, for example, as the base resistor of a simple transistor, and then you know that the photocell, when you shine light on a photocell, the resistance of the photocell, the photocell is nothing but a variable resistor, where the resistance of that resistor changes based on the amount of light that you shine upon the photocell. And so you can put the photocell over here, and then depending on how much light you shine upon the photocell gets, then there is different resistances here. Depending on that, you have different currents over here, and depending on that current, you have different types of currents over here. Depending on that, you have different types of V of C over here, and so on and so forth, right? So that's basically what the transistor does. Now, what's important here is that you can actually use this transistor as a closed mechanical switch, meaning that you can close and open the switch if you can adjust all of these values in such a way that the voltage drop across the collector emitter junction of the transistor is 0 volts. Then in that case, basically the transistor acts as a closed or open mechanical switch, right? So in that case, what you can do is that your V of C has to be equal to 0. So now I'm doing all of this calculation so that you can see that you have all kinds of control over V of C in this circuit. So now in order to basically now we saw that the voltage with these values with these values for R of B, which is 100 kilo ohm, and then R of C was 1 kilo ohm, and the beta of the transistor was 50, and of course the beta has no units because it's a ratio, right? So the R of B is equal to 100 kilo ohm, R of C is equal to 1 kilo ohm, and beta is equal to 50. We got V of C is equal to 5 volts, meaning that half of the voltage of the supply voltage is dropped across this resistor here, and the rest is dropped across the collector emitter junction of the transistor. Now let's make a simple some changes here. Now let's see what happens if I change the beta of the circuit to 75, meaning that if I take this transistor out, and instead of that use a transistor that has beta is equal to 75. So in that case, basically in the first case we had V of C is equal to 5 volts. I can write it down over here. Let me write down everything over here, because that way we can actually compare everything. So I'm going to write basically V of S, which is the supply voltage here, is equal to 10 volts. I'm not going to change that in these experiments. My R of B is equal to 100 kilo ohm. R of B is equal to 100 kilo ohm. R of C is equal to 1 kilo ohm, and the beta of my transistor was 50. The beta of the transistor was 50, and as a result what we got was that V of C was equal to 5 volts, right? So that was basically all the calculation that we did here. Now let's see what happens if I change the beta of the transistor to 75. Now I'm going to change the beta to 75 and see what happens. And of course, naturally logically you can imagine what happens if you change the beta to 75. So using these values, what we got was that when beta was equal to 50, the voltage drop over here was equal to 5 volts. Now if I increase the beta of the transistor, what that means is that since beta is equal to I of C to I of B, if I increase beta, the collector current of course is going to be increased, because per base current, right? Meaning that when beta is equal to 50, then the collector current is always 50 times the base current. When your beta is equal to 75, your collector current is always 75 times the base current, meaning that you will always have a greater collector current depending on your base current. Now imagine that the collector current is increased. If the collector current is increased, of course, what happens is that the collector current increasing, that means that there is more voltage drop across this resistor. More voltage drop across this resistor, that means that less voltage drop across this PN junction, because the voltage drop across this PN junction and the voltage drop across this resistor, when you add them together, that should add to the power supply voltage, because these two are in series and connected to the power supply of the circuit, right? So So what that means is that when I increase the beta of the transistor from 50 to 75, I should get a less voltage drop as VFC, or across the PN junction of the transistor. So let's see what happens in that case. So if I have, so now I can imagine that R of B is equal to 100 kilo ohm, and R of C is equal to 1 kilo ohm, and my beta is equal to 75, and basically my supply voltage is equal to 10 volts, right? So again, you have to do the same thing, meaning that first I have to calculate the base current, then I have to calculate, based on that, calculate the collector current, then based on that I have to calculate the voltage drop across this resistor. Then once I have the voltage drop across this resistor, I can calculate the voltage drop across the PN junction of the transistor, right? So to calculate the voltage drop across the current of the base current, you can simply apply the Ohm's law. V is equal to IR to R of B, and since I have a supply voltage of 10 volts, I can ignore the 0.7 volt voltage drop across the base emitter junction of the transistor. So I can simply imagine that 10 volts is dropped across this resistor, which gives me 10 volts here, and then the current is the current going through the base, and the resistance is 100 kilo ohm, which is basically 100 times 10 raised to the power 3 ohms. So your I would be equal to 10 volts divided by 100 times 10 raised to the power 3 ohms. So then that would be a 10, that's 10 raised to the power negative 4. 10 raised to the power negative 4 amps. So nothing has changed here yet, because the value of beta, when you change it, it of course doesn't have any influence on the base current. It changes the collector current based on the base current. And of course the base current is not going to change as a result of changing the beta of your transistor, and you got the same current before as well. So here I of B is equal to 10 raised to the power negative 4 amps. I of B is equal to 10 raised to the power negative 4 amps, right? Then based on that, you can calculate the current going through the collector of the transistor, meaning that you know that beta is equal to I of C to I of B, and therefore basically when beta is equal to 75, that means that then I of C is going to be equal to I of B is equal to 10 raised to the power negative 4 amps. So that means that I of C is equal to 75 into 10 raised to the power negative 4 amps. That's 75 times 10 raised to the power negative 4 amps. So that means that I of C is equal to 75 into 10 raised to the power negative 4 amps. So I think of course the collector current has increased a little bit, because as I can remember in the previous step when we calculated I of C, it was something about 50 times 10 raised to the power negative 4 amps, I think. Of course I was doing that part of the video yesterday, and I paused the video and I slept, and then, but I'm 90% sure that was the case. Now the current that is going through the collector is 75 times 10 raised to the power negative 4 amps, and I'm going to avoid using milli and micro and that sort of thing. I'm going to, at least for this part, I'm going to basically I'm going to treat this problem as a physics problem, because this way it's easier when you deal with these kinds of things the electronic way. In the electronic way, everything has to be in milliamps or microamps or that sort of thing, and usually you don't use the scientific notation. In electronics, basically your numbers are, for example, 75 into 10 raised to the power negative 3 amps, for example, and then you call this 75 milliamps. And all engineers basically use this kind of language. All electronics engineers use this kind of language. For example, everybody uses 75 milliamps or 80 milliamps or 90 milliamps or 100 milliamps and that sort of thing. But this kind of number is not used in physics. In physics, you have to use the scientific notation, and the scientific notation tells you that, for example, this number is supposed to be written as, for example, 7.5 into 10 into 10 raised to the power negative 2 amps, and then this becomes negative 3 amps. And then this becomes 7.5 into 10 raised to the power negative 2 amps. And that's basically how you show the current. Now, it doesn't really matter. It doesn't really matter whether you call it a milliamp or microamp and so on and so forth. You write your number down this way and then use it in the rest of your calculation and you have no problem. But in the world of electronics, if you give this number to an engineer, it means almost nothing to an engineer. For example, that the current is 7.5 into 10 raised to the power negative 2 amps. People just don't do that. But for the purpose of this video, I'm going to do exactly that, and then we can compare our results, and then we again can, of course, get back to the world of electronics. So now you can see that I of C has increased to 75 into 10 raised to the power negative 4 amps, and of course this way it's easier for me at least to calculate. And then once you do the calculation, you can express your numbers in whatever way that you want, but then once your numbers are not in scientific notation, at least for me, it's not easy to do the calculation. Okay. So now you can calculate the voltage drop across this resistor. You can apply the Ohm's law to this resistor over here. So V is equal to IR applied to this resistor. And you have to make sure that you're using the Ohm's law right. The Ohm's law can be used everywhere, in every circuit, to every component in a circuit. But you have to use it properly in any particular case. You have to know what you're doing with the Ohm's law. Meaning that, for example, when I apply the Ohm's law to this resistor in this circuit, what this means is that this V refers to the voltage drop across the terminals of this resistor only, right? And then this I is the current going through this resistor only. Of course, that current happens to be the same current going through the PN junction of the transistor as well, but that's not important. And this R is the resistance of this resistor only. If you have these three values, if you enter these three values correctly into the Ohm's law in this particular case, the Ohm's law is going to work for you. But then if you basically don't get any of these values right, then of course the Ohm's law is not going to work for you. So you have to use it properly. So the voltage drop across this resistor is therefore going to be I, which is 10 raised to the 75 into 10 raised to the power negative 4 amps, times R, and your R is basically 1 kilo ohm. So 1 kilo ohm is 10 raised to the power 3 ohm. And so that's the same thing as 75 into 10 raised to the power -1 volts, which is the same thing as 7.5 volt. So you can see that now 7.5 volts is being dropped across this resistor. If you and therefore V of C would be equal to 10 volts minus 7.5 volts, which is equal to 2.5 volts. So you can see that the voltage drop across this resistor actually decreased as I increased the value of beta, right? So now I got 2.5 volts over here, meaning that if I change the value of the beta from 50 to 75, then V of C becomes 2.5 volts. Right, becomes 2.5 volts. Now, there is one more thing that we can do here, and that is we can basically change the value of this resistor over here as well, meaning that R of B right now is I can change the value of R of B to basically 250 kilo ohms and change the beta to 75, meaning that all of these values are the same, except that I'm changing the value of the base resistor to 250 kilo ohms, and the beta I'm changing it to 75, right? So let's see what happens there. So when we change the beta to 75, the voltage over here changed to 2.5 volts, right? Now, if I change the resistor from 100 kilo ohm to 250 kilo ohm, what that means is that more resistance that I have over here, more resistance means more voltage drop across this resistor, right? Or in terms of current, that would be, since V is equal to I times R, more resistance means less voltage, less current, basically. Taking the voltage constant, more resistance means less current. If you increase the resistance, you have to decrease the current. Now, since the current is being decreased, then of course you will get less current, less collector current as well, because when you decrease the current over here the current will be decreased as well, because beta is equal to I of C to I of B, right? I of C to I of B. Now, since this is a ratio and the ratio always remains constant because the beta is constant always, so when you decrease I of C, you have to decrease I of B. When you increase I of C, you have to increase I of B as well. So now here we are basically I of B here is being decreased because of the fact that I'm using a higher value for this resistor over here. Higher value of resistance means lower value of current, and so I of B is being decreased, so I of C has to decrease as well. Since I of C is being decreased, what happens is that then there is less current basically flowing through your collector, and then what happens to the voltage across this resistor? The voltage across this resistor is V is equal to I times R. So if you, of course, the voltage is constant here, and when you have less you have when you have I'm sorry, the resistance is constant here. When you have basically less current, you have less voltage as well, meaning that excuse me, resistance taken constant here. When you have less current going through the collector, there is less voltage drop across this resistor. Less voltage drop across the resistor means more voltage drop across this across the PN junction of the transistor, because the two voltage drops have to add up to the supply voltage, right? So now what that means is that, again, you are going to end up with more or less the same 5-volt voltage that you had here, because on the one hand you are increasing the beta. You're increasing the beta, and by increasing the beta you will get less voltage over here as V of C, right? As we saw over here. Now by increasing the value of this resistor, you're going to get a little bit more voltage over here, and so these two voltages will most probably cancel each other out, and then ultimately you're going to end up with more or less the same type of voltage as V of C over here. But let's see actually how that works out, right? So what that means is that now again we have to calculate basically the base current, and then based on that going through the rest of the circuit. So the base current is basically depends on this resistor over here. So basically we have V is equal to I times R, and the voltage over here is 10 volts, and I is equal to the current that we want to calculate, and R is equal to, in this case, 250 kilo ohm, which is 250 into 10 raised to the power 3 ohm, which means that I is equal to 10 volts divided by 250 times 10 raised to the power 3 ohm, right? That's 1 to 25. That's 1 to 25 into 10 raised to the power 3. Now what is 1 to 25? 1 to 25 is 0.04. That's the same thing as 0.04 into 10 raised to the power negative 3 amps, right? And I'm going to write this as basically 4 into 10 raised to the power negative 2 into 10 raised to the power negative 3 amps, which is the same thing as 4 into 10 raised to the power negative 5 amps. So that's your base current. So that means that your I of B is equal to 4 into 10 raised to the power negative 5 amps, right? That's your I of B. Now based on the I of B that you have, you will have some I of C, meaning that you know that beta is equal to I of C to I of B, and that is the same thing as so beta is equal to in this case 75 is equal to basically I of C to I of B, and I of B is 4 into 10 raised to the power negative 5 amps, which means that I of C is equal to basically 75 times 4 into 10 raised to the power negative 5 amps. What is times 75 times 4 is equal to 280, and 280, 300 into 10 raised to the power negative 5 amps, which is the same thing as 3 into 10 raised to the power 2 into 10 raised to the power negative 5 amps, which is the same thing as 3 into 10 raised to the power raised to the power negative 3 amps. So your I of C is equal to 3 into 10 raised to the power negative 3 amps. And of course, I'm not writing the number of significant figures explicitly here, but I know that in all of these cases, I'm going to take basically, for example, 2 significant figures, not more than that. So that's my I of C, and then once I have my I of C, I can calculate the voltage drop across this resistor. The voltage drop across this resistor is going to be applying Ohm's law to R of C. V is equal to I times R. I have the voltage across the resistor is equal to I going through the resistor, which is 3 into 10 raised to the power negative 3 amps times the resistance, which is 10 raised to the power 3 ohms. And then these two will be cancelled out. V is equal to 3 volts. So that means that there is 3 volts voltage drop across this resistor, meaning that the rest of the voltage is being dropped across the PN junction of the transistor. And as a result, there is 7 volts voltage drop across the PN junction of the transistor. That means that V of C is equal to 7 volts, right? Now this way, it seems to be much easier for me to calculate. Otherwise, I would have to confuse myself. So as you can see, there is all kinds of voltages that you can get across the PN junction of the transistor. So you can have 5 volts, you can have 2.5 volts, you can have 7 volts, and so on and so forth. And the way that you can figure it out is again based on the same thing. For example, the very simple rules that you know about these circuits, meaning that, for example, you know that first, the less current that is going through your base, the less current is going through your collector. And also basically, and of course, you know how to control those currents. In order to control those currents, for example, of course, you start from here, from the base of the transistor, and the current going through the base of the transistor is controlled through this resistor over here, R of B. And applying the Ohm's law to this resistor, V is equal to I times R. Of course, the voltage is the voltage drop across this resistor is constant. It's not going to change, so you can keep this constant. Now, if you can see that based on the Ohm's law, that basically that by changing the value of the resistance, you can change the value of the current going through that, because if you increase your R, your I has to decrease, and if you decrease your I has to increase, because these two, the product of these two has to be equal to V, and V is constant here. You cannot change V here unless you change your power supply, which is something that you don't want to do, at least in this particular case. So if I assume that the power supply or the voltage drop across the resistor is constant, then you have control over these two parameters as far as the base is concerned. You can change the value of this resistor. The lower the value of the resistor, the more current is going to go through it. The higher the value of the resistor, the less current is going to go through it. And that's basically how you have control over the current that is going through the base of this transistor, right? Now, once you take care of that problem, then you know, and then And then depending on how much current is going through the base of the transistor, you know that beta is equal to I of C to I of B. And so based on this, you know that the more current that is going through your base, the more current is going to be going through your collector, because the beta over here is constant, and this ratio has to remain the same. Meaning that when you increase I of C, when you increase I of B, I of C will be increased, and you don't have any control over that. When you decrease I of B, I of C will be decreased, and you have no control over that. So by controlling I of B, you're controlling I of C in your transistor. Now, when you now basically all the way up to here, you know how to basically increase or decrease the current in the collector of the transistor. The next thing that you can do is that now the current in the collector is either increased or decreased, right? Now, depending on the decrease or increase of the current in your transistor, there is some voltage drop across this resistor, the collector resistor, meaning that applying Ohm's law to this part of this circuit, to this resistor, if I take this current constant, meaning that this is the value that I'm changing in this circuit, or either I increase it or decrease it depending on my situation, then basically if I keep the value of this resistance constant, the more current that I have here, the more voltage drop I will have here, and the less current that I have here, the less voltage drop I will have over this resistor over here, right? So the more voltage drop here means in turn the less voltage drop over here, because the voltage, the power supply voltage is limited. The more voltage drop that you have across this resistor, the less voltage remains to be dropped across the PN junction, and vice versa. It is basically just like, for example, two resistors in series, and then you connect them to a power supply, and this is V of S, and then V of S, of course, we are assuming that V of S is constant. So if V of S is constant, the more voltage that is dropped here, the less voltage will be dropped here. The less voltage that is dropped here, the more voltage there is to be dropped over here, right? So it's just something logical. And as a result, then basically the more current that is going through your collector, the more voltage drop you have here, the less voltage you have over here, and so on and so forth. And then that way you can basically design your circuit in such a way that you get the desired amount of voltage drop for your V of C. Whether you want to make it 0 or any other value, it depends on your application. So that's basically the whole story there. Now there's only one thing that needs to be talked about here, and that is a condition that we have already talked about, which is called saturation. I think I'm going to end this video here, and we will talk about saturation in the next video. Thank you.